Hi Rudra.
Good evening.
Yeah. So we will wait for a few minutes and then we will start. Okay.
Yes, yes.
Okay, let's begin then today's discussion. Yeah. So thank you for joining. Let me start with the question that you posted last time. Okay. Let's not start with that. Let me start with a few basic things. Yeah. So today's topic of discussion is the today's topic of discussion is compactness. Compactness of a topological space. All right. So now let me first discuss what is open covering. Yeah. So let me first start with discussing open covering of a topological space. Okay. So a collection, call it, let's see, of open sets. Okay. An arbitrary collection in particular. So of open sets UI. I is varying in some uh, arbitrary index set such that their union contains X. okay, contains the whole topological space, is called an open covering of X. All right. So a collection of open sets in the topological space X such that their union is contains X called open covering of X. All right. And we say C has a um, X has a finite subcover of C if there is a finite subcollection, let's call that to be D, okay, containing finitely many open sets from C. Okay, it's a finite subset of C such that their union, okay, this finite union contains your whole space X. Okay, then such a set is called a finite subcover of C. So given a subcover, we can talk about a finite subcover. Okay, but this finite subcover may not exist all the time for a given topological subspace or topological set, right? So when this happens, so now definition of compactness. So we say uh, for a given open cover, there exists a finite subcover for a given open cover of X. There exists a finite subcover of X. Then we say X is a compact space. Okay. So this is the definition of compactness. For a given open cover, there exists a finite subcover. All right. Now, what are the examples you may ask? So some examples we will prove today. Some of the examples, and let me write them as the questions for the easier understanding. All right. So I hope this is clear till this point. Definition of open cover, and then definition of finite subcover, and then the definition of compact set. So now let's discuss some questions. Okay, so these questions will also give you the examples, abundant examples of compact sets. Okay, so let me start with the discrete topology. Okay, examples in discrete topology. So question number one: a finite subset of a discrete topological space x tau is a finite subset of a discrete topological space x tau compact. Okay. So again, I will give you a few minutes to think about this question and then we will discuss the um, solution. All right.
No, sir, it will not be compact.
Okay. Why do you think so?
Sir, uh, if we just consider our, our, let us just consider a space, uh, the whole integer set, and then if we just consider all the even numbers from there, then
Yeah, but it's not a finite set. Set of even numbers is not a finite set.
yes, sir.
So I'm saying a finite subset of a discrete topological space is compact. Even numbers are not finite. Okay, so let me discuss why will that be true. So because it is finite, right? And what is a discrete topology? In discrete topology, uh, so let denote your set to be a1 to an. All right, it's the finite subset. You can index them. Okay, let's index them up to their cardinality and assume that their cardinality is capital N. So it is, we have indexed them. So let this be the subset. Call them to be A. Okay. Now, since X has a discrete topology, yeah, it doesn't matter, right? So now let's start with, so we need to give a finite subcover to a given cover. So let's also assume that, and C, which is a arbitrary collection of open sets, be an open cover of A. Okay. So we started with an open cover of the finite subset. Now we need to find out a finite subcover of this. Okay. So how do we do that? Since there are only finitely many elements, so you can pick uh, your open sets which contains each of the finite, which contains each of the element, and that number will be finite only because there are only finitely many elements. Okay. So pick mm, u I from alpha such that AI contains in UI. Okay, so that's how we are picking and define define a finite subcollection D from U to capital N. All right. So clearly, union of ui contains your whole subset A in it. All right. This may contain more than that. So it at least contains A in that. And it is a finite subcover also. Okay. So A is a compact set in your discrete topology. All right. So,
Yes, sir.
yeah. So, what we are discussing for those who just joined, we are discussing the compactness today. And this is the first question that we discussed. Earlier than this, I discussed the definition of compact set. It is already part of the lecture, so I don't want to repeat that again. So, this is the first question, that any finite subset of a discrete topological space is compact. And the answer is yes, it is. Okay. And now I will ask you a different question once this is clear to you. So let me ask you this question now, which is very much related to the question number one, and the proof is also identical. Okay. So is a finite subset of of a of any topological space compact? Okay. So what I have done here is that instead of considering discrete topology, let us consider any topological space. Okay, any topology whatsoever. So now what happens to a finite subset in in any topological space? Okay, so I will give you again a few minutes to think about this. The answer is in front of you. So you just need to tell me. Okay.
Sir, Gawa,
Your voice is breaking. I can't hear you properly. If possible, you can write also. Yes, that's correct. That is correct. And the argument is exactly the identical. Okay, the solution, the proof that I have given for question number one directly follows up for question number two as well. Why? Because the proof of the question number one, I haven't used the fact that it is a discrete topological space. Okay, you can check that even in the open covers, where the topology will be used, I haven't used the fact that it is a discrete topology. So I'm not using any uh, I'm not taking any advantage of the fact that it is a it is a discrete topological space. So the proof remains identical in this also. Okay. So the proof that I've given is more general. It's for any, it will work for any topological space. All right. Is this clear? Can we move ahead?
Yes, sir.
Good. Okay. So now then in the, let's move on to the discuss few more examples. Okay. So this clearly gives you a class of examples of compact subsets. Okay. In any topological space, it gives you a huge class of examples. Whatever topological space you want to work in. Okay. That can be a norm topological space, metric spaces, or whatsoever. So any finite set, you'll see it is going to be a compact. Okay, so we don't study the compact. So we don't study the finite subset with respect to the compactness. Okay, because it's going to be compact already. So so the infinite sets are the interesting one. Okay, so let us explore the infinite subsets. Okay, what kind of infinite subset? Let us look at some examples in this fine infinite subset. Some example which is infinite or compact subset. Okay, so now question number three. Question number three is that, right, any subset of cofinite cofinite topological space x tau is a subset of a cofinite topological space compact. Okay, so uh, let us just quickly recall what do we mean by cofinite topology. So cofinite topology, let me denote it by tau c. So tau c is precisely the collection of all subsets of X such that their complement is finite. All right. So that's the topological space that you're working with. And the question is that given any subset in this topological space, uh, what can you say about the compactness? Okay, whether it will be a compact or not. So again, I will give you a few minutes to think about this and then we will discuss the solutions. Okay. For those who joined just now, I'm discussing the questions on compactness of a topological space. Okay. I have already discussed the definition and already discussed that the finite subsets of any topological space are compact. All right. I'm recording this session, so you can go back whatever you have missed to in my YouTube channel, and you can have the look at the recordings also. All right. So um, yeah. So question number three. So I give you a few minutes to think about this, and then we will discuss the answer. Okay, so do we have any guesses or something?
Sir, it should be compact.
Okay, good. What about others? Okay, so let us discuss why it's going to be a compact set. Uh, so for finite sets, we have already seen that it is going to be compact. Yeah. Now let's look at the infinite sets. All right. So let a let A be a subset of X, infinite subset. Okay. Yeah. So let's say that A uh, has elements AI where A alpha, where this alpha is in some arbitrary indexing. It can be a countable index set, it can be an uncountable index, and we never know. So it's a so denote this. All right. Now suppose C, which is collections of open sets, okay, be collection, be an open cover of A. All right. Then so let's pick some U naught from this collection C, okay, and consider the complement of this and define uh, the complement of this U to be B, so X minus U naught. Okay, now since tau C is a cofinite topology, and U naught is an open set, so B is a finite subset of X. All right. So B is a finite subset of X. Thus, intersection of B with A, which is a subset of B, is also finite. All right. Now, let us name these elements in the intersection A1 up to some AN. Okay. Now denote this thing. Now consider now take open sets U i's from the collection C such that AI is contained inside UI. All right. Therefore, we get a finite subcollection or a finite subcover of A, which is precisely given by D uh, ui I from 0 to m. All right, and thus hence A is a compact subset of x tau c. Okay. So the idea is pretty clear. We explicitly use the fact that it is a cofinite topology. Okay, so we start with a open cover of this set. All right, so it doesn't matter what kind of open cover we are starting with. It's just some arbitrary open cover. All right, and then we pick an open set from that open cover. Now we look at its complement. We call that open. We call that complement to be B. And now since we are working with a cofinite topology and U naught is open set, so B has to be a finite subset. Now we look at the intersection of B with A. All right, and B intersection A is also going to be finite because it's a subset of a finite set, and we name the elements in B intersection A to be A1 to AM. And now for each of this element, we pick uh, we pick up open set that contains open set from the cover from the initial original cover, so that contains this thing. And these open sets has to be finite because each of them is containing a single point and the number of points that we're looking is finite. So then we get a finite subcover of A. All right, so this implies that A is a compact subset of x tau c. Is this argument clear?
Yes, sir.
Good. What about others? Okay. uh, all right. So let me discuss then. We can move ahead now. So right. So we have discussed that finite sets are compact. We have seen that in any arbitrary subset of the cofinite topology is also compact. All right. Now let us yeah. Now let me discuss the question that Rudra asked last time. Okay. Just give me a second. That will also give us a family of compact sets. Not a family, but yeah, it will give us, will prove that non-compact sets. All right. So let me write down the question. Question number 4. Let X be a metric space of real valued continuous function on the interval close 0 close 1 with the supremum distance okay, the distance between two functions is given by the supremum for all f and g in X. All right. Then this question further defines two spaces. Set of all X such that f of the image of f contained inside this, and z such that such that the image of contains inside in a separation. All right. Um, Options are y is compact, option B, x and y are connected, option C is z is not compact, and option D is z is path connected. All right. So this is a question from a metric topology. Okay. Um, so this is a question from metric topology, and we have given a supremum distance. So this supremum distance is precisely defined by uh, the infinity norm on the set of all continuous function, which takes value in which takes is defined on 0 comma 1 interval and a real valued function. Such a spaces are precisely called to be C0 comma 1. Okay. Set of all functions defined on this and takes real value such that f is continuous. So we are working with this space. All right. And you can give a metric to this by you can first define a norm to this space, and the norm is given by um, yeah. So with respect to this metric, this becomes, let's denote it by d infinity metric. So this is a metric space. In this metric space we are working with. Now, y is compact. So the answer A is not correct. Y is not a compact space. X and Y are connected. Yes, that is true. B and C are correct. D is also not correct. So that's the answer in this question. Now I will discuss the compactness first. So Y is compact. Y is not compact space. So for that we need to give a open cover for which the subcover finite subcover does not exist, right? Um, right. So what can be the open cover? So we need to understand that Y is, how does Y look? All right. So this is a square in which the image functions of Y, images of Y will land. So basically, this square denotes the graph of all functions that are contained in Y. Okay. So yeah, you can draw the graph of functions in Y in this particular square. So we define a function to be like this. All right. So we define the function uh, in this way, such that f1 takes, um, yeah, we define it in this way, that fn takes at m the value 1. Okay, not at m, at 1 over m. Okay, and further, m minus 1 at, um, yeah, m at m minus 1 takes value to be 0, and similarly at m at 1 over m plus 1 it takes value to be 0, and in the middle it is just a straight line joining these 2 points. So for example, half. Okay, so half will take at 1 by 3 and at 1. Okay, so the half, it will be 1, and it will be 0 at 1 by 3, and it will be 0 at 1. All right, so this will be the graph of the function for f2. This is f2. Okay, similarly you can draw for f1 also. So f1 is 0 at 0, 1 at 1, yeah. So what is f1? Yeah, so f1 is going to be defined like this. This is f1. Similarly, you can define f3 by f4, okay, and so on and so forth, and you can go on. So this will give you a family of functions. Call it to be f, fm, uh, in set of all natural numbers. Okay, the index is in the set of all natural numbers. So this is a family of fm that is contained inside y. Okay, now here is this one thing to notice, that fm, distance between fn and fm is 1 if m and n are not equal. Okay, why is that so? Sorry, not one. What is the distance? It is the maximum, right? So it is true, it is 1 only. Yeah. Okay, and why is that true? Because if m and n are not equal, then uh, then for f of m at 1 over m it will be 1, and f of n at 1 over m will be 0. So this value will always be 1, or the otherwise, uh, you can think of it in that way. Okay, so this will always be 0, this will always be 1 if this is not true. And now, uh, we consider, let us consider the ball of, yeah, let us consider some ball of radius, let's say half. All right, let us consider ball of radius 1. Hmm. whatever radius you consider, whatever ball of radius you consider, it will not going to happen. um, yeah, so let us consider ball of radius 1 itself. um, okay, so this is centered at fn and of radius 1. So now this union is obviously contains your y. Okay, this will obviously contain your y because it will be uh, taking one distance you need to go above to the top. Okay, and it already contains that much. So it is already part of, so it will go beyond this block. Okay, so for example, you if you look at one radius, so it will go like this till this point for 0, and for 1 it will go to 2. For 0, for 0 value it will go to 1, and that will contain all the points in that, all the images of the functions. Okay, so this will contain the images of functions of y. All right, so if I do that, okay, now, so we consider this collection of uh, so we consider this collection of, so this is a collection, an open cover of y. Now we need to say that there is no finite subcover of it. And how do we say that? Suppose there is a finite subcover of it, and it can be spanned by a few balls of fi. All right, so suppose there is a finite subcover d consists of finitely many functions, I varying from 1 to n in C, then um, yeah, so okay, so then there will be, Yeah, so we need to say that it will leave out points. It will leave out the some. It will leave out some of the points, right? So that means okay. So suppose if there are 2 points f and fi, then their distance is going to be smaller than 1. But let's say they are contained inside the ball of fi, of some fi. Then we apply the triangle inequality. So the distance between fm and fi and fn and fi. And now this distance is going to be 1. We already know that. All right. So this is going to be 2. So this 2 is going to be smaller than 1, or this distance is 1, but this quantity, yeah, okay. So this gives you a contradiction. All right. And x and y are connected spaces, that again you can see. And the similar argument can be this can be given in the z also. So it is also not compact. Now z is path connected. Z is not path connected because you can see the separation over here. It separates in two ways. So there cannot be a function that is. So you can take a function. So it's some sense it's happening like this. There is a separation at this point. So it is a basically it is separation like this at half. So you can consider a function which takes a constant value half. And now this function, right? So this function will be in the function between the function on the top and function on the below. Function that takes value on the top and function on takes value on below. So now, given any function over here, there cannot be a path that joins this function with the function on the top. You need the function that which is constant at half. So hence it will not be path connected. So this is the answer. Okay. 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 Now let's move on to question number other questions.
That's a doubt, sir.
Yeah, yeah, please.
Sir, so in the first option where y is compact, so sir, we've just
Why is not
proved,
compact? Yeah.
sorry, sir, y is not compact,
Yeah,
and
yeah.
that is because, sir, first we said that there is the union of all the balls.
Right.
Uh, wi- so that is obviously an open cover, but then the
Right.
finite subset of those balls
Will not cover the
will
whole space. Yeah.
understood, sir. Yes, sir.
Yeah. Okay. Question number 5 now. Now, again, which of the following subspecies of R are compact? Okay. So before going into these questions, so till now we have seen the definition of the compactness in a more general setting. Now there is for non-linear spaces, which you might not have heard, but for R and R2 and R3, on which we can give norm, and they are vector spaces. So vector spaces that possess a norm linear spaces called norm linear spaces. On that, you can get a metric topology, and under that you have a Henny-Borel theorem. Okay, so Henny-Borel theorem. So it basically connects closed and boundedness with the compactness. So it says that uh, in non-linear spaces, so let me write it in a simpler way. In R or R2, um, any closed and bounded subset is compact. All right. So I'm not going to prove this. This is a big result. You can find uh, this theorem as well as in your lectures. Now let us discuss some questions based on this thing. So question number one, sorry, question number five. Which of the following subspecies of R are compact? Okay. So first is Q intersection with 0 comma 1 interval, um, 0 comma 1 interval. Option C, 0 comma 1 minus Q. Option D, 0 union with 1 over n sequence. Okay, compact sets. That's the question. So I will give you a few minutes to think about this question and then we will move ahead with the solution. Okay.
Sir, B and D are compact.
Right. So B and D are the correct options. Uh, and this is direct from the Henny-Borel theorem. So because B is a closed set and it is also bounded, so it is compact. Similarly, D is also closed. Why? Because the limit point of 1 over n is 0 and it is part of the set. So it is closed and it is bounded because it is contained inside a ball of radius 1. Okay. Why A and Q and A and C are not? Because for A, it is not closed. Okay. So there can be a sequence for a for an irrational number. Okay. Since Q are dense in nature, so for a irrational number given an irrational uh, R in Q intersection, sorry, in 0 comma 1, for any neighborhood of R, there exists a rational. Why? Because rationals are dense in nature. Okay, rationals. For every neighborhood UN, there exists a rational QN. All right, and this will give you a sequence. So you will get a sequence of QN that converges to R. Okay, as n tends to infinity. That's it. Okay, so you can take this ball of radius, ball centered at R of radius 1 over n. All right, so this is a neighborhood of n, and as n goes to 0, this sequence in this neighborhood you will find root of qn, and this will converge to R. All right, so yeah, so rationals, so the limits of rationals can be irrational numbers. Okay, so it is not closed because the irrationals are not part of this. A similar argument can be given in this. uh, Limit of irrational can be irrational in this way. All right, so this is also not closed. So both are not closed, that's why they are not compact in nature. Okay, I would just like to modify this proof that I gave last time in while discussing the problem suggested by Rudra. So in that I have defined this family. Until this point it is all fine. Okay, now instead of, so let me define a new cover. So consider open cover um, C balls of any function, okay, of radius 1. Not, let's not take 1, let's take 1 by 4. Okay, radius 1 by 4 and x is an element in y. Okay, this is, so this is an open cover, clearly an open cover, and it covers, their union covers whole y, because I'm taking for any point in y, I'm taking a ball of radius 1 over 4. Okay, now let's say it has a subcover, it has a finite subcover, okay, for some xj's. All right, part of this thing. And if I take two functions from my FIs, okay, that I just defined, if I take any two functions, their distance is 1. All right, and since they will be part of some xj because of this x cover, so they will be part of some xj. All right, so their distance, by using triangle inequality, you can apply this. So their distance is going to be like this. So that means, what is this? So since they are part of some xj, this distance is going to be 1 by 4. This distance is also going to be 1 by 4. And this collectively is going to be half. But on the left hand side, I have 1. So this is a contradiction that I was given last time. It was not clear then, so it is clear now. Okay, so I pick a xj which contains uh, more than two FIs. Okay, so pick xj such that uh, fn contains in BD xj1, And this one can do because it has infinite number of infinitely many this, and xj's are finite in nature, so you can always find two of them sitting in one by pigeonhole principle. Okay, so yeah, so this is a contradiction, so there cannot be a finite subcover of this. Okay, so yeah, that was the last part, and this was present question. Any question at this point?
No, sir.
Okay. Question number two. Sorry, question number 6. Yeah, again, which of the following sets are compact in R2? Compact in R2. Option A, the closed unit ball, BD, centered at origin and of radius 1, closer of that. Take option B, the open unit ball, centered at origin of radius 1. Option C, the subspace x sin x for x in 0 comma 1. So it is nothing but basically the graph of sin x in the closed neighborhood 0 comma 1. And option D is the subspace, which is the intersection of where an is a closed bounded in R2. All right. So again, I will give you a few minutes time to think about this question, and then we will discuss the solution. Again, the hint is the Henny-Borel theorem. And let's see.
Sir, only A and D.
A and D. What about C?
Sir, the sine curve is not bounded. I mean, it
No,
is.
but we are looking in a bounded domain, though.
Oh, yes, sir. Between 1 and -1, then yes, sir.
Yeah, so we are looking in sine curve. Graph of sine curve is bounded. That is true, and we are also looking in the bounded domain, compact domain. So
Sir, then ACD.
right, that is the correct answer. Okay, so the proof for A is, again we need to use Henny-Borel theorem. So it is a closed unit ball, so it is already a closed subset. So for A, BD01 is closed, all right, and it is bounded because VD01 is a subset of ball centered at origin of radius 2, all right, so it is bounded as well. So since it is closed and bounded by Henny-Borel theorem, it is compact. Now option B, Option B is open ball, so it is not closed. So it is not closed. But um, yeah, so it is not closed, but we need to prove that it is not compact. That is a different thing. So um, so it is not closed. That means we cannot apply Henny-Borel theorem. But do we have this kind of equivalence that compact sets are equivalent to closed and bounded? So in R2, yes, we do have. So compact set are equivalent to say that closed and bounded. So because of this fact, this space is not going to be closed. So this is another result. So this is another theorem. But this theorem is true only for restricted spaces. It's not true in general. So this is true for R2 at least. Okay. Now Option C says this function. So f is a function from this compact interval to your R2. All right. And it is a continuous function. Okay. And is defined by x going to x comma sine x. So it is a continuous function. It's continuous both coordinates. So it is continuous. So image of a so now there is another theorem which says that continuous image of a continuous image of a compact set is compact. All right. So because of this theorem, uh, your space A is compact, which is nothing but the image of F. Okay. Now option D. Option D is intersection of closed and bounded. So closed and bounded in R2 is compact. So each AN is compact in R2. All right. And uh, arbitrary intersection of closed sets is closed. It is closed because AN are closed. Okay. And this intersection is a subset of AN. Okay. For some N. And AN is bounded. Okay. So so we can use the similar bound, and this is, let's say, containing some ball of radius centered at origin of some radius, let's say capital R. So the same bound happens to be true for the intersection. All right. So it is bounded as well. So it is closed and bounded since the intersection is closed and bounded in R2. That means this is compact. All right. So now let's move on to discuss another question. Question number 7. Again, the question is which of the following are not compact? Not compact. Okay. Option A is an infinite set X with discrete topology. Option B, a finite set X with discrete topology. Option C, a finite set X with any topology. Option D, infinite set X with cofinite topology. Okay, so again, I give you a few minutes to think about this, and then we will discuss the solution.
Sir, only A.
Yes. So we have already discussed last three options that are compact. All right.
Yes.
Now only A is remaining one. Now an infinite set X with discrete topology. So you can give, so suppose, so you need to give a open cover such that there is no finite subcover of that. So suppose X is infinite subset. Okay. Let me denote a alpha where alpha is some indexing. Okay. And now, all right. Um, and now consider an open cover C consists of these singletons. All right. Because each singleton in a discrete topology is an open set. Is an open set. All right. Now this open cover, there is no B. Now clearly there is no finite subcover of C because A is not finite. Because A is not finite, right? All right. So this is a subcover. This is a open cover, which does not have any finite subcover. Okay. So yeah, only A of option A is not compact. Other than every set is compact. Good. Okay. Now let's move on to discuss question number 8. Let X be topological space. Which of the following is true? Any compact subset A of X is closed. Option B, any closed subset A of X is compact. Option C, if X is Hausdorff, any compact subset of A in X is closed. Option D, if X is compact, any closed subset A of A in X is compact. Okay. All right. So again, I will give you a few minutes to think about this, and then we will discuss the solution of this question.
Sir, only C and D.
C and D, you are saying, right?
Yes, sir.
Good. Yeah, that's correct answer. So, yeah, C and D are precisely theorems in your lectures. So these are precisely theorems in your lecture notes. So I won't go into detail of the proof of these things. Now, what I will do, I will give a counter example for A and B. All right, why A and B are not true. So for a compact subset of A is of X, a compact subset A of us X is closed. For that, we need to work with some non-Hausdorff space. And what is a non-Hausdorff space that you know? It is actually the finite complement topological space. So any space with finite complement topology. So let X be a so X tau C. Consider X tau C be finite complement topological space, cofinite topological space. All right. And we know that any subset in this is finite. Sorry, any subset of this topological space is finite. Okay. We know that any subset A of X is a compact subset of X. All right. Uh, okay. So consider for a finite set F, consider FC. So FC is an open set because its complement is finite. Okay. And FC is compact but not closed. Okay. So this gives you a counter example uh, there on. Right now for we need to work with something which is not compact. We need to work with a non-compact space in order to say that any closed subset of that is not compact. So let's work with R. So on R, but on R, closed and bounded implies compactness. Okay, they are equivalent notion. So we need to work with something which is closed and unbounded. Okay, so closed and unbounded subset of. So basically, let's work with R2. It will be easier of R2. And what's an example of that? So you can draw just line. So consider define this subset A, set of all xy, such that x is equal to y. So this is a line, equation of line. Okay, uh, and it is closed. So clearly this is closed, but not bounded. So it is not compact. So A is not compact. So this is an example of a closed set which is not compact. Okay. So B is also false. C and D are statements of theorem. So we don't go into the proof of that. That is part of your lectures. Okay. Any question?
No, sir.
Good. If there is no other question, then we can stop today's discussion at this point. Thank you for joining, and I hope to see you next week as well.
Yes, sir.
Okay.
Thank you, sir.